Alright, so today I'm gonna be explaining another important article with the title Combinatorial Optimization with Automated Graph Neural Networks. Even for graph representation, if we know some information such as commute time and we can obtain it numerically, then we can have an advantage over traditional graph representation learning. So that's why I've selected this special article. So it is in 2024 and it uses combinatorial optimization. So it solves it, but not like classical computer science. We use graph neural network with that. And nowadays we are seeing that, we are observing that these methods that are based on graph neural networks are even better than the traditional approaches that they don't use graph neural networks and are based on optimization, integer programming, mixed integer programming, and those things. So in recent years, graph neural networks have become increasingly popular solving NP-hard combinatorial problems such as maximum cut, maximum independent set. The core idea behind these methods is to represent the combinatorial optimization problem as a graph, and then use GNNs to learn the node of graph representation, graph embedding with combinatorial information. Although these methods have achieved promising results, given a specific combinatorial optimization problem, the design of GNN architectures still requires heavy manual work with domain knowledge. Existing automated GNNs are mostly focused on traditional graph learning problems, which is inapplicable to solving NP-hard combinatorial optimization problems. To this end, we present a new class of automated GNNs for solving NP-hard problems, namely AutoGNP. We present combinatorial optimization problem by GNNs and focus on two specific problems: mixed integer programming and quadratic unconstrained binary optimization. The idea of AutoGNP is to use graph neural architecture search algorithms to automatically find the best GNNs for a given NP-hard combinatorial optimization problem. Compare existing graph neural architecture search algorithm. AutoGNP utilizes two-hop operators in the architecture search space. Moreover, AutoGNP utilizes simulated annealing and a strictly early stopping policy to avoid local optimal solutions. Empirical results and benchmark demonstrate superiority of our proposed model. So this AutoGNP is an automated graph neural network, and the terminology is like we have some edges of the graph, and these are matrices that we will talk. And we consider two NP-hard problems: mixed integer linear programming and quadratic unconstrained binary optimization. So for mixed integer linear programming, you can represent it like this, because I have a playlist called approximation algorithm, which I've talked about this classical computer science thing. Also, for example, stock market portfolio optimization. It's just we want to maximize this penalized objective function. And the vector P and Q here are just unknown, and we should learn it from the data. And the Kubo model can be described as minimizing a Kubo-Hamiltonian. So it's just argmin of X transpose QX. So we can model these MILP instance by a bipartite graph. So let's take an equation. The bipartite graph is denoted by S sub V and S sub C. So some nodes here, it's a bipartite graph. And as you know, there is no intersection between them. So each node, there is no intersection, it's a bipart. The fixed information for node V sub I is a feature vector. So the feature for node C sub j is B sub j, and the responding weights is this A sub ij. Such a weighted bipartite graph can cover all the information that we need for this problem. So you can see how these two are separate. It's a bipartite graph going from SV to SC, and we are minimizing this objective. So you know, each one has a feature. So FV and FC denote the node feature. Node feature of SV group and the node feature of SC group. So once we get a good representation, then we can solve this problem. So they use graph neural architecture search, which is a relatively new thing. I think it is originated in Google when they have lots of resources to do these kinds of heavy optimizations. Optimize on the architecture, which is, it means that you are optimizing over lots of hyperparameters, and each one is a totally different system. So it can be described, most GNNs can be described like this. And for example, graph convolution network is a simple aggregation and update. But in recent years, there exist various graph neural architecture, and they have obtained promising popularity in many applications. So in this part, we introduce AutoGMP, which a differentiable graph NAS framework for solving NP-hard combinatorial problems. For efficiency, we also leverage a bi-level optimization. And so we should note that our objective may achieve an unexpected minimum, and we can involve two optimization tricks. First, simulated annealing. The first one, we would leverage simulated annealing for obtaining global minimum. The second one is a strictly early stopping policy. Different from a default adaptive early stopping, we use a more strict policy for efficiency. Set the stopping patience and threshold as constant in order to avoid failing to local minimum. Differentiable search algorithm. So compared to other reinforcement learning based frameworks, we here consider more efficient differentiable algorithm for search algorithm. You know, it's a decision problem. That's why we are talking about these things. For example, when the gradient and the function value are both close to zero, we prefer to add some Gaussian noise with mean zero and covariance, the trivial covariance, to the function value in order to jump outside the local minimum proactively. So we update the variable in M by approximating the gradient like this. And W is the current operation, and KC is a learning rate of the inner optimization. You know, because you can consider it as a bi-level optimization. And search space for GNN architecture. So similar to aggregation function, the true hop message passing functions to combinatorial optimization are designed like this. So here it denotes a true hop neighbor to node V, which can also be written as node set as follows. So any problem can be written as one of these Hamiltonians. For example, max cut can be written like this. Maximum independent set, you can write it like this. And the experiments show that they have, for different graphs, for example, for this graph, the auto GNP gives this result. And you know, the bold one denotes the best solutions. But their message passing, they use 2-hop. And for performance, you know, we have different problems like set covering, facility location, maximum independence set. For example, maximum independence, I've seen an article that they use it for over smoothing, which is very interesting. I will explain it in one video.